by definition, it's a probability that you reject the null hypothesis using whatever method you're using, assuming the null hypothesis actually is true. Okay, so alpha is a probability of, actually this is something you can phrase in terms of conditional probabilities. It's the conditional probability of rejecting the null hypothesis given that null hypothesis is actually true. It's the likelihood of accidentally rejecting it when you shouldn't have. So what does that mean in terms of these hypotheses? So let's assume that this null hypothesis is true. So then, alpha is equal to the probability of rejecting the null hypothesis. So that's the hypothesis that these things are all equal. At an alpha level of 105. Maybe it's the alpha level that we've cited before. And so let's compare this to what we'd get for alpha if we just compared all the means through a time. Right? The probability of rejecting the hypothesis that just one pair, so let's say that mid-sized cars have the same mileage as SUVs. So probability of rejecting this at alpha of 0.05 is 0.05 definition. Same thing with any of those other pairs. So we have two other pairs. So probability of rejecting the null hypothesis that the mean of SUVs is equal to the mean of pickups. At the same alpha is equal to 0.05. Same thing for the probability of rejecting the last pair of comparisons. So mu mid equals mu pickup is 0.05. Okay, so if we're just running each of these individual tests at this alpha 0.05, the probability of rejecting any one of those is 0.05. But suddenly the probability of rejecting any one of these three, or at least one of these three, is going to be a lot bigger than 0.05, right? If we just look at this one and ask, do we reject it or not, it's a probability of 0.05. But if we're asking ourselves, is any one of these going to be rejected, that's going to have a higher probability. Right, so we're basically asking, we're rejecting the null hypothesis in this case if any one of these three pans out, right? So the probability of rejecting the null hypothesis is the probability of rejecting this first comparison or rejecting the second one. So SUVs equals pickups, or rejecting the third one. midsize, and pickup. Okay. So the actual alpha level that we get if we look at just pairs of hypotheses is this probability, the probability of rejecting the first one, or the second one, or the third one. And, you know, whatever this is, it's basically impossible to compute this. But what we do know is that it's going to be definitely bigger than the probability of just rejecting the first hypothesis. Right? And that we said was 0.05. Right? I mean, there's more ways to reject this thing, or there's more ways for this event to happen than for this event to happen. So definitely this event has a higher probability, which means definitely if we're just looking at a pair of examples at a time, we're going to get an alpha bigger than what we started with. Okay. So this is sort of how you prove this mathematically. I mean, another way of thinking about it, right, is if you have a coin that has a 5% chance of landing heads, if you flip it 3 times, there's going to be a bigger chance of at least one of those flips coming up heads. And so that's basically the problem of multiple comparisons, is, you know, if we repeat this experiment for 3 different things, we're going to get, you know, a higher probability of rejecting, you know, at least one of these than we are for just doing it once. Okay? Any questions on this?
So would that kind of be a form of p-hacking?
Yeah, this is exactly the same principle as the p-hacking thing we talked about. Right, just like, you know, if the probability of getting 4 heads in a row is pretty small, but when everyone in the class flipped a coin 4 times, there's a few people who did get 4 heads in a row. That's because if you repeat this experiment over and over, there's a high chance of it working out at least one time, even if the probability of it working out when you do it just once is really small. So it's exactly the same principle as well as behind the p-hacking thing. Okay. So the main takeaway from this is if the probability of rejecting a true null hypothesis is 0.05, then if you do this thing 20 times, the probability of rejecting at least one of those is much greater than 0.05. Right? Just like if everyone in the class flipped a coin, definitely someone's going to get heads. Even if just flipping a coin once, there's only a 50% chance of getting heads. Okay? So this is sort of like a pervasive problem in statistics. Is you know, anytime we're trying to compare more than just 2 things at a time, we have to worry about this. And so there's sort of an overall philosophy for how you go about comparing many things at a time. And the philosophy is that you always start by doing some overall test to see if, you know, there's significant data saying that there's some difference here. And then once we know that there's some difference, we can delve deeper and figure out, okay, where are the differences? Actually, that's just like the homework problem we just talked about. First, we, you know, tested whether or not there was significant evidence that these 2 variables were independent. Once we concluded that they were not independent, then we delved deeper and asked, okay, why? What's the pattern going on? Okay, so this